When arranged in an alkaline, this is the way they are going to appear. We start from negative 0.76, which is the voltage or the standard electrode potential for the half cell 2. So we are going to determine, and then we go on, followed by negative 0.44 all the way, and then the one which is on the right hand side is positive 0.80. From this, we are going to look for the difference between two closed cells. That is the difference between Roman 2 and 5, Roman 5 and 3, Roman 3 and 6, Roman 6 and 1, Roman 1 and 4, Roman 4 and 7, Roman 7 and 8. We look for the difference and then we determine which one is the lowest. From the calculation of standard electrode potential for the cell, that is the EMF of the cell, this is what we have got. To calculate the EMF, we say EMF is equal to standard electrode potential of the right hand side with less that of the left hand side. Like for example, to get this one, we subtract 0.76 from 0.44. So it is what? Negative 0.44 less negative 0.76. You get positive 0.32 volts. So all these reactions will take place because the standard electrode potential for the cell is positive, meaning that all reactions will occur. So we are going to choose which is the smallest between all these. Now the smallest is positive 0.01. Okay? Positive 0.01. Which is now the cell formed between half cell 6 and half cell 3. So you say what? Your answer will be Roman 3 and Roman 6. A cell is formed by combining two half cells. So we have two half cells. So this one is giving us the lowest EMF. If it was the highest EMF, it would have been very simple. You look for the one which is on the far right and the one which is on the far left. But for the lowest, you have to do calculation. So these are questions that requires higher order thinking. This is what we call a question. Higher order thinking question. Okay? It requires what? Higher order thinking skills. That is why it involves a lot of work. First of all, arranging all the half cells. After arranging the half cells, finding the difference between two which are close together until we get the one which is the lowest. Unlike the one for the highest EMF, whereby you just choose the one which is on the right hand side and the one which is on the left hand side, the far left and the far right. Arrange the metals silver, iron, and tin in order of their reactivity with dilute hydrochloric acid, starting with the most reactive. Give a reason. Now, to be able to answer this question, we are going to find the potential difference between for the half cell of the metal and hydrogen ions. So the hydrogen ion is Roman 1. Okay? As per this equation, hydrogen ion is Roman 1. So you are going to find the EMF for the cells formed between all these metals with hydrogen, and then we find the one which produces the highest EMF is the one that is going to give us, is the one which is going to be the most reactive. The one which is giving us the lowest EMF is the one which is least reactive. Okay? So let us do that. To be able to answer this question, we arrange the metals depending on the EMF that is produced when the iron half cell reacts with what? Hydrogen half cell. So from the equation, we say EMF is equal to standard reduction potential on the right hand side with less standard reduction potential on the left hand side. So from this, hydrogen ions is undergoing reduction. That is why it is on the right hand side. That's why we are writing the standard reduction potential, which is 0.00, with less standard reduction potential of iron, which is negative 0.44. We get positive 0.44 volts. We calculate for tin again. Tin to undergo oxidation hydrogen to undergo reduction. Then you calculate the EMF of hydrogen less that of tin, which is going to give us positive 0.14. And lastly, the EMF produced when silver and hydrogen ions react. So silver to be on the on the left hand side, where we have oxidation taking place, that is silver to undergo oxidation and hydrogen to undergo reduction. When you calculate the EMF, you get negative 0.80 volts. So when you arrange according to the voltage, iron produces the highest EMF, which is positive 0.44 volts, followed by tin, which is positive 0.14 volts, and lastly, silver, which is negative 0.80 volts. So if you arrange them, iron is the most reactive, followed by tin, and lastly followed by silver. If you are told to give the explanation, you say the standard reduction potential for the cell reduces from iron to silver. Or you say increases from silver to iron. And that is the explanation. That is iron positive 0.44 is the highest EMF. Tin 0.14, which is following iron. And lastly silver negative 0.80 volts. And when the EMF is negative for the cell, then it means that reaction does not occur. So what this one is telling us is that silver does not react with hydrochloric acid. Work follow us in TikTok. We are now in Roman 3, part 1. An electrochemical cell is made up of electron number 4 and number 7. Calculate the EMF of the cell. So we look at number 4 and number 7. So number 4 is this one, and number 7 is this one. So how do you calculate EMF? We say right minus left, and you already have the EMF here. Positive 0.18. So how have we worked it out? We say what? The EMF is equal to standard reduction potential on the right hand side with less standard reduction potential on the left hand side. Okay? Right minus left. Now between number 4 and number 7, which one is on the right? Number 4 and 7. Right is number 7. So it is what? Positive 0.52 with less left. That is number 4. That is positive 0.34. We subtract as we were doing last time and we got it right. Is it correct? And that is the correct response. The student has asked a very simple question. Predict whether solid which is in half cell Roman 4 can be placed in a container of Roman 7. Now what we do, we calculate the EMF. If we get the EMF is positive, then it means the reaction will occur. So it means the container will become corroded, and therefore if you place a solution of Roman 4 in Roman 7, the following day when you come, the whole solution has poured out. Why? Because corrosion or reaction has occurred or has taken place. So you cannot place a solution of Roman 4 in Roman what? In Roman 7, because reaction occurs or corrosion occurs. That is between Roman 3 and Roman 7. A continuation of Roman 3. So from what we have already, from the reduction potentials, tin has a greater tendency to lose electrons than copper. So copper has got a greater tendency to gain than tin. So tin to lose electrons, that is to undergo oxidation, and copper to undergo what? Reduction. To undergo reduction. So we are going to do it like this. Tin, this is the equation for tin. So we reverse the equation for tin. So we'll have tin, which is a solid, losing electrons to give us tin ions in aqueous state and 2 moles of electrons. Okay? And then copper, that is copper to undergo what? Reduction. So we have copper ion plus electron to give us copper solid. Good? So before we write the overall equation, we must balance the electrons which are lost and those which are gained. First equation, tin loses 2 moles of electrons to form tin ion. And the copper is gaining 1 electron to give us copper solid. So if 2 electrons were lost by tin, then 2 electrons must be gained by copper. So how do we achieve that? Through what? Elimination. You multiply the equation of copper by 2 and the equation of tin by 1. So the whole of this equation will multiply by this 1 electron here, while this lower one we multiply by these 2 electrons, like this. So the first equation will remain the way it is, because any number multiplied by 1 will remain the same. So this one will just remain the way it is, like this. Let us multiply this by 2. So copper will be 2. This one, electrons will be 2. And the solid that is formed will also be 2. Then we write the overall equation. What is the overall equation? Electrons were lost by tin, and then the same electrons were gained by copper. So it means the electrons are no longer there. So we omit the electrons. We cancel the electrons like that. So after omitting the electrons, we sum the 2 equations. We sum the 2. So let me put a plus in between the 2. We sum. So we start by summing the reactants. So it will be what? Tin plus tin solid plus 2 moles of copper 1 ions in solution. Okay, what do you form? We form 2 moles, we form this one, 1 mole of tin ions in solution and 2 moles of copper solid. So this is the overall cell equation. This is the equation that you're supposed to have. This is the diagram that we obtain. We put hydrogen on the left-hand side. Hydrogen is the one that is doing what? That is supposed to be losing electrons. And tin is supposed to be gaining electrons. The reason why we are doing that is because the EMF of tin is negative 0.14, meaning that the electron flow is supposed to be flowing from tin to platinum. And we don't, because hydrogen is a gas, we use an inert electron, which is platinum, and hydrogen is pumped at 1 atmosphere to the solution, which is containing the 1 molar hydrogen ions. So the solutions that are used are 1 molar solutions. So here we have 1 molar solution of hydrogen ions, which could be any acid. Here we have 1 molar solution of tin ions, and the electrode is tin. But here, since hydrogen is a gas, we cannot have an electrode of hydrogen because hydrogen is not a solid. So instead, we use what? Platinum. So this is the setup. The flow of electrons is negative. So it means this voltmeter will not be deflecting to the right direction, but it is deflecting to the left direction. That's why the voltage is negative 0.14. So to calculate EMF for any of these solids, we calculate it in reference to hydrogen, and hydrogen is the reference electrode. Where it is negative, then hydrogen is on the which side, right or left? Is on the left-hand side. Are we together? If the EMF is positive, like for example in the case of cell number 4, then it means hydrogen is on the right-hand side, and the reading, the deflection on the voltmeter will be to the right. That's why you're having a positive side. I hope that is okay. Always, the flow of current will always be opposite to the flow of electrons. So if electrons are flowing towards the hydrogen half cell, then it means current is flowing from hydrogen to T. In a normal cell, whereby the voltage is positive like these ones, electron flow will always be from left to right. That's the electron flow. What about the current flow? From right to left. That's the flow of current. Under ordinary conditions, when the voltage is positive, like in this case here. Are we together? In these ones, from hydrogen going that direction, then voltage is from, electron flow is from left to right. What about current? Right to left. What about these ones which are negative? Electron flow right to left. What about current? Left to right. So we need to understand. I hope so far you have realized that this number line is very important. If you are in a position to arrange the standard reduction potentials of the half cells from left to right in the right order, there's no question you cannot be able to answer in electrochemistry. Whether drawing the diagram, whether drawing calculating EMF, you'll be able to do all of them.